Alright, so in this video I'm going to work through this problem in the chapter 9 PowerPoint, which many of you are having trouble with. Okay, so let's see how we would do this problem. So what we have here is a frictionless pulley, which is in the form of a uniform solid disc. And the mass of the pulley is given, it's capital M. Radius of the pulley is also given. And there is a rope that goes over, that's wrapped around the rim of the pulley. Just make it match the diagram in the PowerPoint. And there is a stone attached to the other end of the rope. The system is released from rest. So the question is, what is the velocity of the stone when it has descended by a height of 1 meter? So there are multiple ways of doing this problem. Once you learn about torque and angular acceleration, you can apply Newton's second law to do this problem. But this problem is in the chapter 9 PowerPoint, so the only method that you know that is available to you if you have only studied up to chapter 9 is energy conservation. And that's probably the better method of doing this problem. So we're going to apply conservation of energy. We want to find the velocity of the stone when it has descended by a certain height h. So when the stone is over here, we want to know what its velocity is. Okay. So let's just set h equals 0 at the bottom. And let's use conservation of energy. The equation of conservation of energy is k initial plus u initial plus w other equals k final plus u final. Okay. So the initial kinetic energy, the whole system is released from rest, as the problem says. So there is no kinetic energy to start with. What about the initial potential energy? So the only thing whose potential energy changes is the stone. So we just need to consider the potential energy of the stone. Our reference level for potential energy is the ground, h equals 0. So the potential energy of the stone is just mgh, little mgh. There is no friction or air resistance or anything, so we don't have a W other to worry about. All right. Now, when the stone has reached the bottom, what is its kinetic energy? Its kinetic energy is half little mv squared. Okay. But now the pulley is also rotating. So the pulley has rotational kinetic energy, and the formula for rotational kinetic energy is half I omega square, right? Then what is the potential energy of the stone? The stone is now at height 0, and so it doesn't have a potential energy. And the potential energy of the pulley never changed, so we don't care about that. So that is our equation. There's only one thing we need to figure out, which is what do we do with this omega. So the logic that we use here is the following. The velocity of the stone is v, right? That means every the stone is connected to the rope, so that means every point on the rope has the same velocity v. So if every point on the rope, okay, I'll write these down. Velocity of stone is v, right? That implies that every point on the rope has velocity v. So that would mean that a point on the rope which is in touch with the pulley also has a velocity v, right? And so that's this point. This point also has a velocity v. So, but this point is in touch with the pulley. So that means the pulley has a tangential velocity v. And this is assuming that the rope is not stretching or slipping. And that's almost. So this is assuming the rope is not stretching or slipping. And that's usually the case. So once you know the tangential velocity of the pulley, you can find its angular velocity by using the relationship that v tangential is equal to r omega, right? So that means omega is going to be v tangential over r, but v tangential, we just agreed, is just v. So now you can just plug that in to the equation. So mgh is equal to half mv squared plus half the I of a cylinder. I'm just trying to see what shape. Yeah, it's a solid disk, so that's a cylinder. So the I of a cylinder is half mr squared from the table of moments of inertia, and omega is v over r squared. So we can just go ahead and work this out. Mgh is equal to 1/2 mv squared plus 1/4 capital M. The r squared cancels out, v squared, right? And so if you multiply both sides by 2, you get 2 mgh is equal to m plus capital M divided by 2 v squared. And so from there you get v is equal to the square root of 2 mgh divided by m plus capital M divided by 2. And that is the answer. Okay. What is the acceleration of the stone? So that is simply a kinematics problem. So the stone started with 0. So this is part B. We are just going to draw the stone here. It started with initial velocity 0, and it got a final velocity. V initial is 0. V final is what we just calculated, right? The distance that it traveled is h. So what is its acceleration? So to find that, you would just use the third kinematic equation. V final squared is equal to V initial squared plus 2a times the distance, right? And you would solve for a from there. V initial is 0. V final square we just found is 2 mgh divided by m plus capital M divided by 2 is equal to 2a times h. The h cancels out, the 2 cancels out, and so you get acceleration is equal to m divided by m plus capital M divided by 2 multiplied by g. So you can see that its acceleration is not going to be g. It's g multiplied by a factor less than 1, because little m divided by little m plus capital M over 2 is less than 1. So it would accelerate downwards, but not quite at 9.8 meters per second squared. It would accelerate slower than that, because the pulley is unwinding as well. What if the pulley were extremely light? So we can just do a special case just to make sure that what we calculated makes sense. Suppose the pulley is massless. So in that case, massless meaning very, very light. So if the pulley is really light, then it won't have much kinetic energy. So in that case, m tends to 0. What happens if you let m tend to 0? Then a would be approximately equal to g, So that makes sense that if the pulley hardly has any mass at all, then the stone would just fall at with the acceleration due to gravity as if it's just freely falling. All right, so that's all there is to this problem.